So the next topic is, or the first advanced topic, is traffic controls on the grid. So we have seen an example in the quiz where the absence of traffic control could cause some trouble. For example, when one of the smart meters was creating trouble. Traffic control in the internet is solved by two things. The major one is the concept of congestion controlled sources, which goes together with the fact that traffic in the internet is so-called elastic. Elastic means the actual throughput you get when you do a Skype call, when you transfer something from a website, is not predetermined. It depends on the state of congestion of the server and of the internet and of your local computer networking infrastructure. This is okay for most things, not really okay for some audio-video applications. For Skype, if it breaks, the audio breaks because there's too much video, you need to switch the video. So one of the problems of Skype and similar communication is really this, is the absence of traffic control, but we learn to live with it. For industrial applications, of course, we need more. We need delay guarantees. For example, 4 milliseconds. This is the delay guarantee we need in the smart grid. I would say in the smart grid, this is the most stringent delay constraint we have. In other environments, like when you control a car with electronic, for example, when you send a signal to the brakes or to the accelerator or to the motor, if it's an electric car, or to the engine or to whatever, or if you fly by wire in an Airbus or even a Boeing, then you have even a stricter delay, so sub-millisecond delay. And also no loss. Losses can, of course, always occur if we send data over a physical thing. You can never be 100% sure that there will be no loss, but you don't want to have packet losses of 2%, for example. You want that those are rare events that hopefully the logic of the application will be able to cope with it. So we want to avoid delays and losses. Where do delays and losses come from? Problems on the physical layer. Yes, so that's a loss could be due to this when you transmit over a wired or wireless infrastructure. So you have propagation of signals, which is something probabilistic. We hope the coding is good, is adapted to the channel, etc. But you cannot guarantee that there are no losses. Of course, this is very different if you have wired Ethernet, for example. Here the losses are extremely rare on the wires themselves, because you have good quality wires. When you have power line communication, it looks more like wireless communication. Losses are, the channel is very bad and so harder to control. And when you have wireless communication, then it's even worse. It's more difficult to control. Why is wireless communication more difficult to control? Exactly, because typically the medium is changing. If you do point-to-point wireless communication with directional antennas, then you will have fairly good communication as well. So this is done in some long-distance links where you have, you can see that in the mountains sometimes, you can see antennas that are very directed. So you can send a wireless signal with beam forming so that it's very concentrated, and then you will have quality that's very close to that of a wired system. But when we use wireless for this Bluetooth device or for in the room, then the channel is the room, for example. So the room is changing because your head is moving, your fingers are moving. So whenever things are moving in the room, then the channel changes. Also, of course, things are not static. We have the optimal coding and the optimal management of the channel would require to know exactly the channel, which we do only approximately because my Bluetooth device here is always the same. I take it with me. So the fact that the things are mobile or changing is what makes the thing worse. So that's one of the reasons, but there are other reasons. On Ethernet, I said if we use cables, there is quasi no loss. Still, we might have losses in a system that uses Ethernet. Congestion, exactly. So congestion losses are the major causes of losses when outside the wireless channel here. Because we've seen that the internet is in fact a large queuing system where packets can be dropped when buffers overflow, and this is the major cause of packet losses. So this we can avoid by managing the buffers here. Right? So that's what we said about losses. About delays, then there's not much we can do if the delay is due to propagation. But of course, together with losses, if you want to mitigate the effect of losses, one could be tempted to put buffers, large buffers, into routers and switches. But large buffers will have a drawback of large queuing delays. And eventually, they will not solve the problem of losses. Right? If there is congestion, if you have, remember your babbling idiot meter that is sending more than the capacity of the lines, the problem is not solved by putting a large buffer. Putting a large buffer will only delay the problem. If the babbling idiot is a transient thing that happens during 1 second, a large buffer will solve the problem. But if it's constant, it will just make things worse, in fact. You will have the same amount of losses, except for the transient period during the buffer is full, and you will have the very large delay after that. So buffers are not a solution to problems. In fact, very often they are part of the things that make of the problem. They make delay very large. So we need to do something to manage and control the amount of data that's in the buffers. Right? So that's exactly what traffic engineering is about. So it's about controlling delays and losses in buffers here. So one solution is to give priorities to the critical flows. For example, here, a typical situation is in a smart grid. For example, think of a substation. I have critical flows, the sensors that sense critical states that must give their information very quickly. And I have a large amount of non-critical flows. I have the video surveillance, for example. I have also the software updates that can be done. When we will talk cryptography, we will see also that cryptography has key update, etc. So there is always some amount of background information. That's in the best case. In the worst case, you have an operator in the telestation that's on the web, browsing, buying something at Digitech or whatever. So those things also happen once you have computerized things. So typically, critical traffic is small in volume, but important, and you have a huge amount of best effort traffic. Right. So one solution is for the critical traffic to give priorities. What is priorities? Well, priorities mean that a router would have two queues, one for priority 1, one for priority 2, and the best effort traffic would be put in the low priority, which would be priority 2 here. So here is the classical terminology about priority queuing. So priority queuing is found everywhere in industrial networking, as soon as you have something that uses a network, and comes in two flavors, non-preemptive or preemptive. Preemptive is very complicated and is really for very small infrastructure, so I will talk about non-preemptive. Preemption has to do with what do we do when a higher priority packet arrives and there is a low priority packet that is being served. Do you interrupt the low priority packet or not? If you interrupt it, we say it's preemptive. If we don't interrupt it, we say it's non-preemptive. Now, interrupting packets is very complicated because typically it means I have started transmitting the beginning of a packet, I stop, so I must find a mechanism to allow for transmissions of fractions of a packet. That exists. It's primarily for low speed networks. If you're at very high speed, if the time to transmit an entire packet is short, then you don't bother doing that. So that's interesting, but we will not discuss this here. So we will talk about non-preemptive priority queuing. So a non-preemptive priority queue is, for example, on the output of a buffer here, I'm showing 4 priority level. Priority 1 means it's like in the train system, it's first class, so it's high priority. 2, 3, 4 is less priority. Then the server does the following. It always looks at priority 1 queue. Whenever the server is finished sending a packet, it visits priority 1. If there is a packet to serve, it serves it. Only if there is nothing to serve in priority 1, when the server asks the question, which packet should I serve, only then it will visit priority 2. If there is something in priority 2, it will send it, etc. So priority 4 will be served only at cases where the server has nothing to do, then visits all these, the 3 queues are empty, and then priority 4 will be served. So this is priority queuing, and I'm showing here an example where I have packets A, B, C, D, E that arrive in this order. We see that packets A, C are served first, then packet B arrives at about the same time as A, so it needs to wait until the queue number 1 is idle. There is a gap here. A, C have been served, so B can then be served. Perhaps D also arrives shortly here, so it can also be served, and E will be served after D in that case, because when E arrived after D was already in service at Q2. What we would like to do is analyze in detail what happens in such a queue, in particular for the high priority traffic. So for this, it is convenient to analyze delays, to draw not things like I drew in the previous image, packets that arrive, but to draw curves like this one, the red and the blue curves. What are those curves? They are called cumulative arrival and departure functions, so they're cumulative functions. So the red curve, A of t, is something that time t starts at an arbitrary starting point, which we call 0. This is the time when the system was started. And A of t is the number of bits of this flow that we have observed between time 0 and t. So it's an integral of all the packets that you've seen counted in bits here. And d of t is the same when I count at the departure here. Why is it interesting to do this? Because if I plot this, I immediately see 2 things, delay and backlog. Delay, here if I plot the red curve and I draw a line t, at line t there was the end of a bit of a packet that has arrived here, and I ask the question, when did this packet leave? When did the last bit of this packet here leave the system? Well, if the system is FIFO, if it serves the packets in the order for this flow, then this bit will leave when the number of bits that are left is equal to the number of bits that have come in. Here I'm assuming there is no loss in the system. So we see the delay by the horizontal deviation between the input and output curves. Our interest is in having a delay bound, so whether there is a delay bound that is satisfied or not will be very easy to be seen. We're also interested in having enough buffer. We must show the buffer, we don't lose packets because of buffer overflow. Here we also see the amount of data that is in the buffer. This is called the backlog. At time t, how much of this flow is in the buffer? Well, this is everything that has come in minus everything that has come out. The difference is what is stored in the system. So that's red minus blue. It's A of t minus D of t. So this is the vertical deviation between those 2 curves. So those 2 curves are, this way of presenting the system is interesting because of this. We see here very clearly, and we can analyze mathematically the differences here. I showed a stylized version, which was a very smooth thing. In reality, if we have packet arrivals, we'll have less beautiful curves. I'm showing here for this example what it gives when I do this analysis. I'm showing 2 things. I'm showing the cumulative arrival and departure function for flow 2 and for flow 1, where I call flow 1 and flow 2 all the traffic that goes into, respectively, priority 2 and priority 1. So this is the input here of flow 2. At some time, at the beginning, there's packet B that arrives, so it corresponds to a discontinuity, a jump. I'm assuming packet B is 1000 bits, so there's a jump of 1000 bits that comes here. And then at this time here, packet D arrives, so there is another jump here. So this is the red curve. So it's discontinuous. If we do classical analysis, it's unpleasant, but for the kind of things we do, there will not be a problem with discontinuities. And in blue, I'm showing what I observe if I would do with an oscilloscope. I observe the bits as they move on the line at the output. And we see that the packet B had to wait until A and C are served. So it will wait some time. And this time here is when packet B starts being serviced. Now, since B is transmitted at a constant bit rate, it gives this line here, this linear function here. In reality, it's not linear. If we do a very, very fine-grained thing, it's still discontinuous also. We send the data by, if we really do it with an oscilloscope, we will see chunks that represent one or several bits together, but I ignore those kind of subtleties. At, I would say, a fairly accurate description, we have this. This is how the data is flowing out, and we see that where the horizontal distance in from the red to the blue, that give the time here. So from the beginning, the arrival of this packet until where I reach here the blue line, this is exactly the time for the packet to be transmitted here, which is given by the gray line here, D. Here we saw also the packet D that has arrived a bit later, but it has arrived in the middle of transmission of packet B and before anything is available for priority 1, so it's transmitted back to back, so that gives the output. The blue is the output here of the flow 2. We can do the same thing for flow 1. We see there are two packets A and C that arrive one after the other. They are, since they are high priority, they are served together, so the output is at the line rate here. Then we see that the blue and red curves superimpose, which means the backlog is 0. The buffer is empty for priority 1, which means that this is when we can serve priority 2, which is exactly what happens. Packet B is being served here. Packet D arrives here when the queue of priority 1 is empty, so it starts being served. Then packet E arrives. And packet E here, we see that there is no preemption, so it to wait for the leftover of the low priority to be served. So it will not be served immediately. There is some delay to wait. Then it's served at the rate of the line. And we see what is the delay of packet E. So if we do microscopically the analysis for this flows, this is what we see here. And I can, of course, apply the same analysis to anything that I call a flow. For example, I did here for the aggregate of flows 1 and 2. So if I look at them together, I obtain this as input, and I obtain that as output here. So this output is typical of a constant rate line. So it's a queuing system where the output is at a constant rate, the input is variable, and we see that as long as there is something to serve, the input is at a constant rate. We see here the duration of the busy period, which is from the beginning to time 5, for example. The busy period is when, or the backlogged period is when the red is above the blue here. Voilà, so that's the framework, how we put things together. What we would like is to do a bit of simple calculus to be able to provide guarantees. So the first thing to do that is to precisely define what a rate guarantee means. In the case I gave before, if I look at the aggregate of all inputs, and there is only priority 1 and priority 2 in this simple example. The lower priorities have no traffic. So we see that the aggregate of everything receives a rate guarantee, which is the rate of the line, C here. So in simple case, what a rate means for a line is simple to understand. It means every t delta every duration t, the line is able to serve CT bits, and will serve CT bits if there is enough thing to be served in the buffer. Of course, it will serve less if there is nothing in the buffer, which is what happens here. But we would like to give a more general definition of this. For example, if I have a system that is more complicated, such as what happens to priority 2? What guarantee do we give to priority 2? So for priority 2, intuitively, we could say the line is at C megabit per second. If priority 1 is not a lot of traffic because it's the critical traffic, if it's, for example, C, the line rate is 10 megabit per second. If priority 1 is only 10 kilobit per second, then we think that priority 2 has a guarantee of 10 megabit minus 1 kilobit per second. Roughly speaking, this is true. But when we do delay analysis, things are a bit complicated because we have things like this. We had here, for example, we had delays that are due to other packets. So the guarantee is only roughly speaking like this. If we want to give a strict and rigorous meaning, one way is to use what is the definition of a strict service curve. So we say that an arbitrary system offers to a flow, so we consider a flow, which can be anything, for example, the priority 1, or a given flow inside priority 1, or the aggregate of 1 and 2. So anything you tag as a flow, in and out, and we say that the system offers to this flow a strict service curve beta, that's a function of time, if the following is true. During any backlogged period of duration tau, the number of bits that leaves the system is at least beta of tau. So a backlog period is a period of time during which there is at least one bit of this flow in the system. So this is a period of time where the input minus output is positive. Of course, if there is nothing here to serve, we don't require anything. For example, a constant rate, a line that has a constant rate and only one flow to serve, guarantees beta of tau equals C tau, with C is the line rate here. Because it's true that during any period that is backlogged, if I take any period during this interval, the output is at rate C, is equal to C times the interval. Of course, that's not the only example. If that would be the only example, we would not have such a complicated definition. For example, if I have C here guaranteed to the aggregate, but I have multiple priorities, which service curve is guaranteed to the high priority flow? The parenthesis is missing here. Should we see the solution? So who says A? 0%. Who says B? 0%. Who says C? 0%. Who says D? 25%. Who says E? 75%. Well, let's see the solution. The correct answer is D. Of course, we would be tempted to say A, but there is the preemption, right? If there would be no preemption, the answer would be A. If I have high priority and whenever a packet arrives, we stop everything else and we serve you, then it's as if the others did not exist. So the answer is your guaranteed service is the line rate. But there is preemption. So what happens due preemption is that a high priority packet can find a low priority packet being served before its service starts. So how long can this interruption last? Well, it depends on the maximum size of the packets of low priority. And this can happen only once at the beginning of a backlogged period. So if there is a period of time, like here, we look here at this period where packet E has arrived, then it can be delayed, but this can happen only once in a backlogged period, because if the thing is continuously backlogged, when the server comes back to this queue, it will serve the queue immediately, because there is a backlog. This interruption can only happen because when the server visited the queue, there was nothing in the high priority queue. So it means that during an interval of time where the high priority is backlogged, we are served at the rate C minus an interruption that is at most one packet of the low priority, which means exactly this function. If I draw this function, that means I can be interrupted for at most 1000 bits, or strictly speaking 999 perhaps, but to keep things simple, let's put 1000, assuming the size of the maximum size is 1000, and then I can be served at the full rate. So what is this function? Well, we can write it as CT minus 1000 plus, where the plus means the maximum of 0 and this function. So the maximum of 0 means whenever this negative, we put 0. So that's the answer. That is the strict service curve that is guaranteed to the high priority flow. We see that it depends on the low priority flow only through the size of the low priority flow. So if you peeked over to the next slide, you have the answer to the quiz. So the answer is here. That's a general theorem. If I have a non-preemptive priority scheduler with output rate C, the flow of all high priority packets is guaranteed a strict service curve given by the function we've said before. Right? A function of this type is called a rate latency function. Rate latency means it's a constant rate shifted by some duration t, which is called the latency. So that's our first example of a strict service curve that is not completely trivial, and that makes exact sense of what it means. The high priority traffic is guaranteed a rate C, but there is an impact of latency. The true guarantee is a rate C shifted by an amount T. The proof is in the lecture notes, but I won't go through it. If you're interested, you can go through it. It's all elementary math, so the proofs are easy to do. The rate latency service curve is one that is very, very often used when we do traffic engineering and exact calculation of delays in industrial networks. So it's useful to think of it, have a mental model that is perhaps more physical. We've seen an example of a server, of a flow that was interrupted, but in general we can think of it as a server with vacation. A server with vacation that serves a unique flow is by definition a server that serves at a constant rate R, and when the server is idle, it can go on for vacation for a time at most T, which is exactly what happened in the case we saw before here. So this is a common concept in the queuing theory literature. When you model in reality an industrial controller, for example, very often you have situations like this where you know when a flow has to be served, the server may need some time to finish some action that it was doing, that is called a vacation, and that guarantees that rate latency service curve. That's only half of the story. The second half, if we want to restrict delay, we said we want to give priority to critical traffic. For example, put it as priority 1. But priority alone is not sufficient. Priority is okay if we are sure that the PMU sends one packet every 20 milliseconds, for example. If we don't know how much traffic the PMU is sending, giving it high priority will not necessarily mean that it will have a good delay. If it sends a huge amount of data, and if we guarantee 1 megabit per second with high priority, then if it sends more than 1 megabit per second, we'll still have a problem. So in order to have guaranteed delay and no loss, we need to guarantee a rate through a strict service curve, but we need also to guarantee a bound on the volume of traffic that a source is sending. This is captured mathematically by the concept of arrival curve. We say that a flow has an arrival curve alpha of tau if on any interval of duration tau, the number of bits of data that I can observe on this flow cannot exceed alpha of tau. Right? So over any sliding window of duration tau, we cannot have more than alpha of tau. For example, if I know that my PMU sends one packet of 1000 bits every 20 milliseconds, I could deduce from that an arrival curve that is this function here. This is a linear function shifted. Now the rate latency service curve was an horizontal offset. Now we have a vertical offset. We know that instantly it can send 1000 bits. This is when one packet is sent. But before sending a next packet, you will need to wait for a time that I can calculate here, which is 1000 bits every 20 milliseconds. So it's a slope of 50 kilobits per second. So I know that the second packet will not come before the time it takes for this slope to reach 2000 here. This is not the best arrival curve I can put on that. I could be more accurate if I want, because I know it sends exactly one packet every 20 milliseconds. So after 1000 bits, I know nothing will come, so I could put a staircase function. I could do this, and sometimes it is done. But if we want to have fairly simple things, it's simpler to have linear functions like this here. In many cases, it will give the same result. So by simplicity, we use this. This is called a leaky bucket arrival curve. We will see why a bit later. Just record this name here. So what we've seen here is that if a PMU sends one packet every 20 milliseconds, for example here, that means exactly that over any sliding window, I've put here, for example, two sliding windows, one that starts at time 20 milliseconds. If I plot floating axis over tau milliseconds, I see that I will never have more than the green line here. The same thing if I put this here, anywhere. It looks a bit complicated. It's a complicated way to capture the fact that it sends at most 1000 bits every 20 milliseconds, but the reason is the following one. If you remember what we had with our arrival and departure cumulative functions, we saw that we could see the delay by the horizontal and vertical deviations. When we have the same thing, if we are in the space of time windows, we were before, when I talked of the arrival function A and D, I was in the absolute time space. Here I talk about time windows. And we have this theorem, which is very simple, but is our first network calculus theorem. If we have an input that is constrained by an arrival curve alpha, and if this input goes through a system that guarantees to it a strict service curve beta, then I can plot the curves alpha and beta, compute the vertical and horizontal worst case deviations. What are the worst case? For the vertical, it means I look at the difference alpha of tau minus beta and I take the max. That gives me the vertical deviation. And I know that this will be an upper bound on the backlog. So the maximum amount of data that I can see over any execution of this system will always be less than this vertical bound. Same thing for delay. If I plot the horizontal deviation, which is easy to do graphically, a bit more difficult to define mathematically, the mathematical definition is here, is the max of the duration delta t such that alpha of tau is equal to beta of tau plus delta t over all possible tau here. This is a simple definition when the functions are continuous. If they are not, it's a bit more complicated. But intellectually, it is simple. It's the horizontal worst case deviation between the two. Similarly, we know that if this quantity is calculated, the delay for any packet or any bit of the flow A will never exceed this quantity here. So this is how we engineer systems. We put arrival curve on the traffic. For example, in case of PMU, we analyze what the PMU is doing and we say that's the worst case that can happen. We put a strict service curve on the service that it offers, for example, because it's high priority, and from that we will have the delay. Let's do it. For the high priority flow, we know the strict service curve is given by the blue line, which is a slope C offset by L max over C, 1 millisecond in this case. Now if I take an arrival curve for a PMU, which will give me, or for a flow here, I'm assuming it sends at most 3 packets of 1000 bits every 3 milliseconds, so it's not a PMU, it's another traffic here. That gives me this red arrival curve. The offset is 3, that's the maximum we can send, and that is sent every 3 milliseconds. That gives me the slope here. Then I compute what is the worst case deviation between the two. Now the red and blue lines are parallel, so the deviation here increases when we start from 0. If we go up, it's maximum here and it stays at the same value there. So the maximum is given here and the maximum is 4 milliseconds in this case here. So we know every packet of this flow will have a delay of at most 4 milliseconds here. So this is how we can, in a simple way, find worst case delay here, or bounds on worst case delay. This is a very contorted case that in practice we would probably never do. There is something a bit special here. Do you see what? Yes, the delay is constant here, which comes from something very weird with this system. We can interpret the slope here as the rate that is guaranteed to this flow, with some latency. There may be periods where it's not guaranteed, but over the long term, this is what is guaranteed. The red rate is also something that can be interpreted easily. That's the long-term rate at which this source is generating traffic. Here the two are equal. So you send a source of 1 megabit per second into a node at 1 megabit per second. So it will just work, but of course, if anything goes wrong, it will not work, right? So you're just at the limit where it works. So as a good engineer, you should not operate at the limit. Why? Well, because there are always zillions of little details that are not in the model. Like, is the rate really 1 megabit per second, or is it not 0.999 megabit per second because there are empty slots that are used for resynchronization or whatever? So that happens. Or is the clock of the server exactly the same as the clock as the source? Probably not. If the source is 0.001% faster than the server, this will break somewhere. So that's a very special case. But in theory, if all clocks are perfect and if all your numbers are perfect, this will work here. So now let's assume we do the same thing, but we upgrade this to 10 megabit per second instead of 1 megabit per second with exactly the same numbers as before. What happens to the delay? Are we ready to see the solutions? Who says A? No one. Who says B? No one. Who says C? One. Who says D? One. Who says E? Then 50%. Okay. Well, we need to do the calculation. It's not something that can be guessed. Oops. So it's a very frequent case and very easy. So network calculus is not very difficult. If I have a leaky bucket arrival curve and a rate latency service curves, then the worst case is here at the knee of the leaky bucket. So the problem now is a Math 101 exercise. Calculate this distance here. So this distance is this one plus B divided by the slope of this one. So it is L max over C, or T, the latency in general, L max over C plus B over C. So that's the distance, that's the value here. Now if we keep B, which is the burstiness of the source, it's called the burstiness, that's the max number of bits it can send instantly. This was the same. L max, that's the size of the packets of the interfering flow, of the low priority. The only thing we've changed is C. So if we multiply C by 10, then the delay is divided by 10. So that's why we find 0.4 here. Okay, let's do it again. We downgrade now to 0.1. So this, which was 1 originally, then became 10, now becomes 0.1. So we divide by 10. What happens to the delay? So let's see your answers. Who says A? 50%. Who says B? 0%. Who says C? 0%. Who says D? 50%. No. Who says D? 25%. Who says E? 25%. Well, the correct answer is none of the above. The delay bound here is infinite. You're right. Congratulations. Well, because what happens in reality is this is the drawing we would have here. Right? This rate is larger than the rate there. The rate of the source, which is the worst case rate, is larger than the rate provided, guaranteed. So of course, this system will not be stable. The backlog will accumulate. If the source really sends everything that we think it could send, the server is not able to serve fast enough. The source is at 1 megabit per second. The server is at 0.1 megabit per second. So the backlog will explode. What will happen in reality will not have infinite delay because infinity does not exist on Earth. So what will happen in reality in a case like this? Well, there will be buffer overflow. There is a certain buffer which is finite. Then it will fill and then we'll start dropping packets, which is what we would not like for the PMU. But if the buffer is infinitely large, the delay would be infinitely large. Okay, we have seen the main ingredients with which we can do traffic guarantees. But there are still some issues. Here, we saw that if for the very high priority traffic, which is the critical one, we give high priority, that solves the problem of this flow, except if this flow has a problem, right? Even the critical traffic may have problem. We wanted to protect the critical traffic from problems that are due to non-critical traffic. But what if one of the PMUs or one of the sensors starts sending a huge amount of traffic here? Then what will happen is that flow 2, which is lower priority, will have very large delay. For example, if we're in the case that we had before, that the rate of the high priority traffic is larger than the rate of the server, then all the other low priority things will be denied service. So that's an issue. Right. One solution to that is to prevent things from happening at sources. That is called shaping. Shaping means we think that the flow has a given arrival curve, and shaping means we enforce that. We make it happen. So a shaper is a device that needs to be added to a source. A shaper has a parameter, which is the arrival curve that we want to enforce. And the shaper is something that makes sure that the output, the thing that goes on the line, satisfies the arrival curve constraint. And if the data generated by the source does not, then you buffer them until you can deliver them. Typically, you need to do this buffering because the data is provided by a microcontroller that has also some random times to access memory, etc. So even something that reads one packet every 20 milliseconds might not generate it exactly every 20 milliseconds. So we call shaper mathematically anything that does this, and the greedy shaper is the optimal one. The greedy shaper is the one that delays the packet only as little as is needed. A very frequently used shaper is the token bucket filter that's implemented in Linux traffic control with this command, for example. It works as follows. It's called a token bucket because of this imaginary representation. It's imaginary in practice, it's just mathematical calculations, but you imagine there is a virtual token bucket associated with the buffer of your shaper. The token bucket contains data units that are in the same size and the same units as your data here. Right. Originally, the bucket is full here, and in order to be allowed, a packet that comes here in the buffer must consume an equivalent amount of tokens from the bucket. So if a packet arrives here, if the bucket is empty, then the bucket has to wait, the packet has to wait until there is some token. Now the tokens are magically generated at a rate R. So imagine there's an infinite source of tokens that pours into the bucket at rate R here, right? Until the bucket is full. When the bucket reaches the level B, then it stops. The source stops or it spills out, so the bucket doesn't fill anymore. So let's see a simulation, a small cartoon. Originally the bucket is full. Let's assume I have, and the bucket has 4 tokens of 1000 bytes. So the token are not packetized, but I just show them in blocks of 1000 bytes to make things simple. It's just one value. So it has 4000 units in the token bucket, and I have 5 packets of 1000 bits that arrive. So what will happen is originally, well, the first 4 packets in the buffer can consume 1000 tokens each, so they are released. The first 4 packets leave here. So the shaper allows the 4 packets to go. Then the 5th packet has to wait until there's enough token. Now the token are generated spontaneously at a rate R. So after some time, that depends on this value, L5, 1000 divided by R, there will be another token, enough token here, and the packet will be released here. So the effect of this token bucket filter is to allow a burst of 4000 bits, but then after the burst to allow only a rate of R to be sent. So intuitively, it looks like it is allowing this arrival curve that we had sent that had an offset of B, which is the size of the token bucket, and a rate of R, which is the rate at which the token bucket is replenished. And this is exactly true. So the token bucket filter, if it's initially full, is exactly the shaper for the arrival curve R tau plus B. So the things fit together well. In practice, very often, if we want to put arrival curve constraints, we will put linear arrival curve constraints. And if we want to enforce them, we will use token bucket filters that are easily implemented. They are implemented in all Linux-based operating systems, for example. Here's the proof, which is elementary, but I skip. If you're interested, you just look at it to see. You don't need to have the high-level maths. The proof only relies on the ability to compute minimums, so it just means of things, so you need to manipulate minimums. It's called min plus or max plus algebra. So let's apply that. Let's assume now we're a bit smarter in our network, and we have flows on which we have put token bucket filters, like we should do if we are in an area where we want to control delays and latencies. So I assume the flow 1, which is the high priority flow, has this parameter, 1 megabit per second, and a burstiness of 3 kilobit, etc. The parameters are given for the 4 flows. The line is at very high speed, 1 gigabit per second, and there is no preemptive priority of 1 over 2, etc. Can you give a delay band now for flow 1? Okay, are there some convergences? Let's see your solutions. Who says A? Who says B? So A was 25% and B, A was 33% and B 66%. The correct answer is B. Right. Well, it's just a straightforward calculation. We need just to do the maths correctly, which of course in a short time is always error prone. The high priority receives a service curve with rate 1 gigabit per second and with a latency that is 12 kilobit divided by 1 gigabit. The flow 1 has an arrival curve with rate R1, which is given earlier, and B1. So if I do the math, I need to add the Lmax and the B1, which is 15 kilobit, divided by C, that gives 0.015 milliseconds, so 15 microseconds, which is the kind of timings you care perhaps in flight control, but in smart grid this would of course be a very, very small delay. Okay. That's for the high priority flow, which is not surprising that we gave the high priority to a single flow with this very low rate over a 1 gigabit per second line. What happens to the other? I mean, if I am the priority 2 flow, I probably also have a good service. But this can be true only if priority 1 is guaranteed to not send too much traffic. Right? If priority 1 sends at 1 gigabit per second, things will look bad for priority 2. So mathematically, if I want to find a service guarantee for the lower priority, I must assume some constraint on the higher priority, which we did not for lower priority, right? We assumed only maximum packet size. So here, we must assume that the higher priority flows are limited. So in practice, we will assume, for example, there is a general theorem. We will assume arrival curve for the higher priority flows, but I will give only the simplest form of this general theorem. I assume that the flows, in particularly the high priority flows, are constrained by a token bucket filter with rate Ri and Bi, which means that it's the same as saying that we assume that they have arrival curve constraints with a linear function with rate Ri and burst Bi. Now we zoom on flow I. Then the condition for things to be good is that we must be sure that the sum of the rates of the higher priority is less than, I put equality, but in practice we would not like to have equality, must be less than the rate of the flow C. Right. Then if this is true, we can guarantee to flow I a rate which is the difference of the two, which is of course 0 if there is equality, not very interesting. So the difference of the two gives this quantity here, but the rate is not guaranteed as a constant rate, but as a rate latency service curve. Of course, there is an interruption that can be due now to the max packet size of this flow itself, but also of the sum of the burstiness of all the higher priority flows. So it's not very difficult to accept. The high priority flows go first. The maximum impact they can have is the sum of their burstiness here. It's not entirely obvious, but it's not very surprising either. So take-home message, if you are priority I less than the top, you are guaranteed a rate which is the leftover from the high priority rates, which is the rate of the server minus the sum of the rates of arrival of the high priority, and the latency, which is the sum of the burstiness of the high priority, plus your max packet size, divided by the leftover rate here. So of course, if there is equality here, there is no guarantee on latency, right? I said it's not entirely obvious. I give the proof in the lecture notes, which are not very difficult. I'll let you discover if you're interested. Instead, what we will do is we will apply this here, for example, to flow 2. Again, with the same parameters, 3 kilobit of burstiness for flows 1 and 2, 1 megabit per second of rates for each of the flows. And we must be sure that this is enforced. So we must put a shaper at the sources. Right? So if this happens, we know that priority 2 is guaranteed a rate which is 1 gigabit minus 1 megabit, so 999 megabit per second here. Yes?
In the formula for the latency, why is it not the packet size of the flow with higher priority, with the higher priority instead of the, so L max I instead of L max I minus 1 or?
So in the formula, why do we have L max I here?
Instead of the flow of
the higher priority. So the interruption due to the high priority is entirely included in this. So the packet size doesn't matter.
Okay.
But there is a self-interruption of the flow in itself here.
It's the transmission time.
Yes. Well, you have to look at the proof to understand why. It's not entirely obvious, but that's the thing here. There is a better theory if we can improve on this theory if we don't use strict service curve, but another concept of service curve that will give a different formula, but I don't want to go into those complicated theory. Here the proof can be done manually, it's given there. And if we want to be sure, we have this here. So if we go back to priority 2, here we see that the rate is 999 megabit per second with a latency given by this here, B1 plus Lmax. This is the Lmax of flow 2, which is the same of all flows here, divided by the rate here. So if we want to find a delay bound for this flow, I need also to know the arrival curve for this flow, which is a burstiness of 3 kilobit per second. We know that the delay bound doesn't depend on the rate at which the source sends traffic, as long as this rate is less than the guaranteed rate, at least for linear arrival curve constraint. So here that's the case. The rate of the source, 1 megabit, is less than the 999. So the formula works here. We found 18 kilobit divided by 999, which is the 900 or 1 giga doesn't make a lot of difference, 18 microsecond here. So this is the delay we can guarantee to flow 2. So this is how we can use priorities, token bucket filters, in order to give delay bound. So in industrial networking, you, for example, in complicated networks that are used in Airbus, you have up to a few thousand flows, and then there is, to each of the flow, we give a given priority, and there is a nonlinear optimization problem, which is which priority to give to which flow, such that the delay bounds of every flow are satisfied. So there are other problems which are known in optimization. That's an NP-hard problem, so it's not solved exactly for the optimal, but there are good heuristics. Here I showed only 4 flows. So this is typically the state of the art, how things are done to provide very strong guarantees. We've done it for flow 1, 2. For flow 4, what can we say? So what does the jury say? Who says A? No one. Who says B? No one. Who says C? One. Who says D? Two. Majority says D, which is the correct answer. Well, it's just, we need to sum up all the burstiness of all the higher priority flows and of this flow, plus L max divided by the rate. Now the rate that is guaranteed is the leftover rate, a bit less than 1 gigabit per second. So 218 kilobits divided by this, that's 222 microsecond. So nothing special here, just to make sure you follow the formula. Of course, we see that the lower the priority, the worse the delays are. However, in everything we've done so far, we've assumed we have a single switch, right, which is not really a network. Now, what happens if you have the second switch or second router? In this calculation, switches or routers. Questions on? No. Yeah. Everything's fine.
No, I used the wrong folder.
Okay. Okay. In the buffers I've shown before, I did not say whether it's a switch or a router. I mean, it's from the network calculus viewpoint, there's no difference. Right? So whether you have a switch or a router here, there will be no difference. Sometimes there's a difference in the sense very often the switches are very fast so that you can forget about them, and the routers are more bottlenecks. So very often this is done at routers, but not always. So it's completely independent. What happens when I have a true network? For example, the red flow here, I compute its delay, then it goes to another point here. And of course, at this next router, there will be other flows that come here. And some of the flows that come from this router might go to other routers here. Right? So here, what can I say if I want to do the same calculation? Can I do it again? Well, the answer is no, because if I have a flow that is shaped, for example, with a maximum burstiness of 3 kilobit and a rate of 1 kilobit per second, when it goes through a router, at the output, it may become more bursty. Right? Can you imagine why that would happen? Well, imagine you have, so this flow is sending 2 bursts of data with an interleaving of 20 milliseconds or 3 milliseconds in the example we had before. So it sends a burst of B1 packets, of B1 bits, and 3 milliseconds another burst of B1 bits. Right? At the source, we know those B1s, they can occur only every 3 milliseconds. Assume now that when the first burst comes here, it has the worst case delay. The worst case delay is in this case because there is a packet of low priority that is being served, or more generally, if it's a packet of arbitrary priority, all the other things are concurring so that it gets the worst case delay. That corresponds to the bound we gave before. But of course, this worst case, the worst is never certain. In fact, the worst is very uncertain. If you do simulations, you're very unlikely to see the numbers we see here. So when we do network calculus, it is because we want guarantees. We want to be sure that the delay will never be more than that. If you want to get the worst case delay by simulation, you need extremely, extremely long simulations where you see all the possible random cases that may once occur. So the second burst, for example, might be more lucky. For example, all the other flows are silent during a few milliseconds. So the second burst will have 0 delay, or just the delay it needs to transmit it at 1 gigabit per second. So I'll have a first burst that will wait a number of milliseconds, and the second will not wait. But if I look at the output here, I will have 2 bursts that are closer together in time. So the fact that the service that you give is random, sometimes equal to the worst case, sometimes bad, sometimes good, that makes the output more irregular. So the burstiness at the output has increased. Okay. So what should we do if we have a network here where we want to study everything, where one thing we can do, we can compute bounds on this increase in burstiness. I showed network calculus bound on delay and backlog. The same kind of reasoning can be used to calculate what is the worst case increase in burstiness, and then we can do that everywhere. That's one technique that works and is done, for example, in Airbus. But another technique is to do what we call reshaping. You put another token bucket filter, the same as you had at the source, you put it here at the input of the next flow. That means that in the case where we had two bursts that were back to back, the first burst will be delivered, but the second burst will need to wait a bit here at the shaper. And there is a mysterious result, that is, if you do this, you do not increase the worst case delay bound. You delay the second burst, but only because the first burst, because it was a lucky second burst. So what the shaper is doing is making everything to the worst case. So there is a result which is not at all obvious, but you can find it in this resource, that says that if you reshape, you recreate fresh traffic, so it's very easy. Instead of calculating the burstiness increase everywhere, you just do local calculations that are easier. It's easier to calculate, that means your control plane is simpler, but you need a device. You need to activate the token bucket filter here. If you have it in Linux anyhow, then it doesn't cost much to activate it. And it will not increase the worst case delay. So the delay will be the sum of the delay at this node plus the delay of this node. The delay incurred by the reshaper is not to be added. So the delay that the reshaper adds is a delay that could have happened already. So we'll not see that in detail, but that explains how we can handle networks that are a bit more complicated here. I spoke about delay. Let me talk also about backlog or buffer sizing. Delay is critical. That's really in real-time applications, making sure you get this packet within 4 milliseconds, including the propagation time. That's really the hard thing that's critical. You must also make sure that you don't lose packets so that you have enough buffer. When I say delay is critical, it means buffer computation are also critical, but typically we can live with approximate calculations because buffer today is not such an expensive resource. So to guarantee zero loss, we must make sure that the nodes have enough buffer. We still need an upper bound. We still need an idea what is a conservative estimate. So one estimate is this vertical deviation between the two. So if we guarantee to every priority, if we use priority, to every flow in general, a buffer size that's given by this, there will never be buffer overflow. So we'll never lose packets simply because there is buffer overflow. The calculation is very simple. Let's do it here. If we look at flow 1, the high priority flow, that is this arrival curve and receives this service curve. I plot the two, the red arrival curve, in blue the service curve, and I look at what is the worst case vertical deviation, which is also the supremum norm of the difference of the two functions. So if I take red minus blue, then it's very easy. If I start here, I see that this increase is here. At this point I have a certain value, and if I go beyond, the blue slope is larger than the red slope, otherwise the system doesn't have finite delay, and therefore the maximum is obtained here. So it gives this value. The maximum buffer that is required is B1, the burstiness, plus the latency, T1, multiplied by the rate of the source here. For delay, we saw that the rate of the source did not play a role, but for backlog, it does here. So for example, here we see we will need at most 3 kilobits of buffer here. which is minuscule, so there will be no loss if we do this, even with whatever size we want. Let's retake our last pass on our example. Now I look at the aggregate of the 4 flows together. Right? All the 4 flows together, and I ask, what is the total amount of buffer in the worst case that I will need for this? How would you go about it? Let's do an interactive solution.
Maybe the worst case would be every time there's a lower priority flow that's served just before higher priority flow comes.
Perhaps, but how do we know if that's the worst case? Yeah, but that's a good point. One way to reason about such system is to imagine the worst case. You say the worst case is this, and then analyze what happens at the worst case. This is not what we do in network areas. We don't imagine the worst case. We just put envelopes on everything. We put a maximal envelope on traffic. We put a minimal envelope on service. And we say, if the traffic is really within the maximum envelope and the service within the minimum envelope, then the backlog and the delay cannot exceed this. So we take an exterior approach. We put envelopes, we look at what the envelopes say. We don't know whether it's the worst case. In general, it is not, because, for example, we put an envelope which is a straight line instead of a staircase function. So there are suboptimalities we do when we do this. So we're not sure whether it's the worst case, but we're certain it's a bound. When we do the worst case, is certainly when all things happen together. It's very often true, but to prove that it's true is non-trivial, usually. So the only techniques I know that work well to prove it's true is to do both. We do the outside envelope, so we say, if we have envelopes, we cannot exceed this. I think the worst case is that, and if what I find, what I think is the worst case is equal to the envelope, then it must be the worst case. Very often it's impossible to know what's exactly the worst case, right? Finding the worst case is a very difficult thing. It's an NP-hard problem, even for small systems. For this with 4 queues and things, it will have hyper-exponential computing time to find exactly a bound of delay that is the worst case. But the worst case you will find will be within 0.001% of the bound we found. So we don't bother about that. But here I'm asking for the aggregate of all the flows here and the backlog. So how can we reason about the aggregate? Well, we can reason about the aggregates, but we need to do the 2 envelopes, the traffic and the service. In terms of service, what can we say? When I look at the aggregate, it means I do things like we did at the beginning, I think, when we had this. Here I did the aggregate of flow 1 and flow 2. Now if I ignore that there is priority with the 2, I don't know why packet D is served here and packet E and not the other way around. If I ignore those things, or I don't know why packet, so I have A, B, C. So if I don't know why which packet was served, I have perhaps a non-FIFO system. I mean, if I look at it as a black box, I just look at the packets in and packet out. I ignore the priority. I just see 5 packets in, 5 packets out. I see it's a non-FIFO system because of the priority order. But still, I know a strict service curve. I know that this system is work conserving. It does its weird priority thing, but during any backlogged period of duration tau, it serves at least at a rate tau. Right? The aggregate. Right? So I know a service curve for the aggregate. So if I want a backlog bound, if I want a delay bound and it's not FIFO, it's complicated. But if I know a backlog bound, I don't need the FIFO assumption. I have a service curve. So let me go back to my slide, which is number Yes, so if I go back to this, I have an aggregate. If I look at this as one macro flow, I know this macro flow receives a strict service curve given by the straight line 1 gigabit per second with no vacation, no latency, no interruption. I still need an aggregate envelope for the arrival. What can we say? If I have 4 flows, each of them is individually constrained by token bucket RIBI, can I say that the superposition of the 4 flows also satisfies some arrival curve constraint? Well, the answer is yes, and this is precisely why we use those things. If every flow is constrained with RIBI, then the aggregate is also constrained with the sum of the rate and the sum of the burstiness. To see why, we can do the math here. If a flow I has a arrival curve alpha, the superposition of the n flows has a arrival curve, sum of the arrival curves, which is almost trivial. Right. Because that's a bound on the number of data units you can see over a window of size tau. If you count not one flow but n flow, then you see at most the sum of all the things for every flow. That's trivial. The thing that is interesting is that if we use linear functions, then a sum of linear functions is a linear function with a rate sum of the rates and offset or burst sum of the bursts. This is why very often we use leaky bucket arrival curves rather than staircase. Adding staircase functions is a nightmare. It's a combinatorial problem if the periods are different. Right. It gives complicated steps which are arbitrary. But those things are completely trivial. So if I have flow 1, 2, 3, 4, I can take the sum, which gives 112 megabit per second and 206 kilobit per second. I know the aggregate satisfies this constraint. A strict service curve is given by that, so I do the vertical deviation. That gives 206 kilobit, which is the max I will need for the aggregate of the two. So this is how we can have an idea of the buffer size we require for an aggregate, for example, here. We could have thought of an alternative solution because we were able to compute a service curve guarantee for every flow. We did that for delay. Right? We did it for flow 1, flow 2, and flow 4 in the quiz. If we have a service curve and an arrival curve, we can compute also a delay bound. So I did it here for the 3 here, backlog bound, sorry. So I did it for the 4 flows. This is the maximum amount of backlog of any of the 4 flows that can be present in the system. Therefore, if I take the sum, it is certainly an upper bound on what we can find. Find that the sum is 218 plus something kilobit per second. The interesting thing is less than the sum of that can be found for the sum of if we do a global analysis, which is very typical of any bounding technologies. We put envelopes, we look at the max. We're not sure it's really the worst case. Here we have the sum, the max of 4 things. We know that the max of a sum might be less than the sum of the maxima if the maxima do not occur at the same time, which is one of the reasons that can happen here. But the difference here is very small. Voila, we have done, I'll say, the mathematical theory that is behind traffic engineering in industrial applications and in some elements of smart grids, the ones that is related to critical flows. We have seen that we need some kind of scheduling. We've seen priority. Priority is an example of a scheduling. Scheduling is a mechanism that is implemented in a router or a bridge to decide which flow to serve. The default scheduling is FIFO. I take whatever is first in the queue. But when we do quality of service, we have other scheduling mechanisms. We've seen what is called static priority without preemption. That's one of the schedulers. And we need also to have arrival curves and enforce them, for example, with token bucket filter. There are many other schedulers that exist. In particular, the priority system has a drawback that it requires the token bucket filter to work, right? Which is okay if we have high critical flows. But sometimes people prefer to have a scheduler that is safer per se. So those are called schedulers that are in the family of generalized processor sharing. One of them that is also implemented in Linux is called deficit round robin. So with deficit round robin, it's a bit like weighted fair queuing. That's similar. Did anybody hear about weighted fair queuing? I'll explain weighted fair queuing first. Assume you have to serve packets, and you say, I have 3 flows. Then I can say I give a weight of 1 packet to flow 1, 2 packet to flow 2, and 3 packet to flow 3. And when the server visits Q1, it will serve 1 packet. Then it will go to Q2, it will serve 2 packets, etc. So we allocate to every queue number of packets that we serve. And when we visit the queue, we serve that many packets of the queue. That is weighted fair queuing. Weighted fair queuing. So fair queuing is when the value is 1. I visit every queue and I serve 1 packet of the queue. Weighted is when we give weights. So that's the simplest of all schedulers that has the property of isolation. Deficit round robin is like weighted fair queuing, but it accounts for the fact that packets are not all of the same size, so it's a bit more complicated, but mentally speaking, it's the same. What is the major difference between something like deficit round robin or fair queuing compared to priorities? Well, there is some amount of isolation. If I have a weighted, let's say, take the simplest case where the weights are 1 to all flows. Assume one of the flows misbehaves and sends a lot of traffic. What will happen is that the server will do a round and will still serve 1 packet of this flow at every round. So the effect that is at every round, this queue will have something to serve. But still, I guarantee, if I have n flows, I guarantee a rate in average of C over n to each of the individual flows, regardless of what others are doing. When I say guarantees a rate of C over n, you could easily imagine that what I means is there is a strict service curve that we can compute for weighted fair queuing that has a rate of C over n and the latency, which is a big formula that we will not give here, but that can be computed. So this is what is done in practice. We don't do it because we have only so many hours to talk about it. This is a bit more complicated than static priority. Static priority is found, requires token bucket filters to be put everywhere. Deficit round robin does not require token bucket filters to protect other flows, but of course might still need it to protect if we on delay bound for the flow of interest. So what is often done in practice is that we have some kind of scheduler like deficit round robin that is associated to the high priority classes with a given weight that has to be given to every class. And then there is one class which is best effort for TCP traffic, where we don't put token bucket filter. So there is no guarantee, but TCP will adapt to the rate here. In practice, there are a number of technologies that implement the ideas that we've seen here. In the context of smart grids, it is called IEEE TSN, time-sensitive networking, or IETF. So IEEE is the Organization of Electrical Engineers. I hope you are all members of IEEE. If not, it's not too late to become a member. You just need one of your professors to sponsor you or another member to sponsor you. It makes also standards. So Wi-Fi, for example, is standardized by IEEE. Typically, it makes standards for everything up to the MAC layer. And the internet does standards for everything above. Now, since deterministic networking or network address applies to both, then both standards are specifying how to do it. So what they specify is, for example, which specific schedulers one would like to have, what are the parameters, how to compute the delay bounds, etc., and the shapers, and etc. So this is what is typically happening now and will be, it's new, it's coming now, so it's will accompany the technologies that are done in the smart grid. Of course, there are zillions of other ways you can do it. I mentioned that in Linux we can do token bucket filters and static priority, so you can simply write a program that will do it for you. So this is the ad hoc or software-defined networking way, which is, I would say, what is done today. If you run a smart grid today, you do this. If emerging technologies will be doing that here. We will talk about MPLS also a bit later. Voilà, that's the end. I think I'm 10 minutes late because I was hoping to redeem the break that we didn't do. So in summary, for traffic control, you need to do things like token bucket filter to limit the rate of a source in all circumstances. And together with schedulers, or for example priority, this gives you delay and loss guarantees, assuming you do the calculations, of course. This alone doesn't provide anything. And those calculations of delay and loss guarantees are made based on the concept of service curve in general. We saw the strict service curve, which is the simplest definition, and the arrival curve, right? And the take-home message is, if somebody says, I guarantee a rate of 1 megabit per second, in practice, we don't know exactly what it means, except if we think of that's the rate of service, it means a rate latency service curve. If it's a rate of emission, the rate at which we send traffic, it's the token bucket filter rate here. When we are at very small delay constraints, millisecond or up to 20 millisecond, and low speed, 10 megabit per second, which is typically the industrial environment, then it's hard. So you really need to do all those calculations, and you need to optimize the priorities and everything to achieve what you do. That's the technology, for example, in Airbus. They run at 10 megabit per second. They have delays of 1 millisecond for actuating the flaps, etc. So you do this kind of things. If you run a 5G core network, where some link speed are at 1 terabit per second, then you do much coarser things. So you will do perhaps you guarantee a maximum amount of traffic, and then you guarantee the delay for the worst case of any packet, and you find perhaps 20 nanosecond. And if it's 20 nanosecond, you don't care about it. It will be within your safety margin at the end. So when you're at very high speeds, you still need to verify the rate guarantee. A very coarse latency value of the rate latency service curve will be sufficient. You still need to make sure that even if you're at very high rate, the input rate is less than the rate that is guaranteed. But then, of course, the delay bound calculations need not be so accurate. Still need to be done, but they don't need to be so accurate. Voilà, that's the end for today. Friday, the lab is separated for the two groups, and the lab is in this room, INF 019, not the room that was for last week. Voilà, bon appétit à tous.